This video is one that we're having to sneak in between two others. I did not plan on having to take two videos for the previous one, so this is the back half of what was the first video. The video before this one was where we went through finding the moment of inertia of a uniform rod about its central axis, and that turned out to be 1/12 ml squared. In this video, we ask if instead the axis were as shown over here, instead of it being at the center, it's at that location, how would the moment of inertia about this new axis compare to about its center? And the answer is it's going to be greater. The moment of inertia in this case is going to be greater because the moment of inertia is always a minimum whenever you have a center of mass axis. The more mass that is farther from the rotational axis, that's going to increase your moment of inertia. And here we have bits of mass that are a good distance away from the axis compared to before. So we should get a larger value for our moment of inertia when we do this problem here. So let's go ahead and do that. Here's our axis. Once again, we've got our little mass dm right there, which is a distance r from the rotational axis and has an infinitesimal thickness dr. The moment of inertia is, we're going to integrate here r squared dm. And in this case, we used symmetry last time, but we can't do that here, at least not easily. We're going to integrate from r is equal to negative L over 4 to r equals positive 3L over 4. You can see the picture there in the upper right. Once again, our differential and our integration limits do not agree. And so we're going to have to resolve that again. And the way we did that last time was we said the mass of this uniform rod divided by its length has the same ratio as the mass of dm divided by that tiny thickness dr, which means that dm is equal to m divided by L times dr. So here we go. Let's see if we can flesh this out a bit more. We're going to go from negative L over 4 to positive 3L over 4 r squared m over L dr. M and L are constants, so I can pull those out of the integral. When we integrate r squared dr, we get 1/3 r cubed, and our integration limits are 3L over 4, and down here the lower bound is negative L over 4. So what do we get when we do that work? Let's continue right over there. Let's keep our m over L. I'm going to keep the 1/3 out there for a second. When we cube 3L over 4, that's going to give us 27L to the third over 64. Minus, let's cube this thing. That's going to be, if we cube that, we're going to get negative L cubed over 64. Those then give us an essential plus. This looks to me to be 28/64. 28/64 L cubed. Can we reduce that? How about a common factor of 4? So that would be 7/16. And then I've got an L in the denominator there, which cancels out one of these here. So I'm seeing, let's multiply these out. 7 in the numerator, 48 in the denominator. 7/48 ml squared. Now, what did we say initially? We said that this should be a larger value than what we got when we went about the center of mass. We got 1/12 ml squared. How much would that be? 1/12 would be 4/48, right? Now, We're not going through the center of mass anymore, so our moment of inertia definitely does increase.